Okay, in this video, I'm going to start talking about Module 8, which is the empirical formula. Uh, empirical formula. And then in this video, we're going to try to cover two things. One is what is empirical formula, obviously, and second of all, what is the percentage composition? And you might be wondering why are these two topics even related, right? But we'll explain that later, okay? But first of all, let's look at the example I'm showing here. Now, when we talk about chemical composition, we usually present chemical composition of any chemicals, okay, especially compounds using a chemical formula such as this one, HNO3. Now, you can quickly challenge yourself by, pause the video, see if you can figure out the name. Okay, so the proper way of naming any compound, like I mentioned before, is recognizing what type of compound this is. It's an acid. Okay, because there's a hydrogen in the very front of the molecule. So it's an acid, and you should recognize that acid has a positive one charge, the hydrogen. Like in this case, it's positive one here, and the rest of the molecule should be the anions, and then this is a polyatomic anion. So this is H composed by H plus and nitrate. Okay. So the whole name, the acid name of this whole thing is going to be nitrate turned into ic acid. So it's going to be nitric acid. And because of the oxygens in the molecule, so you should never say hydro. So, all right. So anyway, but that was a review of nomenclature. Okay. Now, what is the percent composition? Well, we know by looking at the formula, it's composed by one hydrogen atom and one nitrogen atom and three oxygen atoms for every one molecule of this compound. But we should also take into consideration how is the mass percentage of each element, or so-called mass percent composition of each element. The way you calculate this is very simple, okay? Now, you're basically trying to get the molecular weight of the whole thing. Think about getting the molar mass of hydrogen, nitrogen, and the oxygens and add them up. And make sure you take in this factor of 3 for oxygen. Okay, so you can obtain the molecular weight of this compound, which is going to be 63. Now, in every 1 mole of this compound is going to weigh this many grams, and also in every 1 mole of this compound, there are going to be one hydrogen which weighs this much grams. So you're going to take the hydrogen mass portion over the total mass of this compound in 1 mole times 100%, give you the percentage, the mass percentage of a hydrogen element. And similarly, you can calculate the mass percentage of nitrogen. You see there's one nitrogen, and that's the molar mass of nitrogen, and 3 oxygens. So you can calculate the percentage of each element. So we call this percentage or mass percent composition. Okay, all right, so let's take a look at a quick example. Okay, we're only going to go over one example of how to calculate the mass composition of a compound. So let's say you're given this compound, right? We've seen this kind of compound before. It's called hydrate, and this is basically composed by ionic compound part plus, okay, this dot is like a plus 6 water molecules. Okay, you can parenthesize this, showing that the 6 applies to the entire water molecule. Now, the question asks you calculate the percent composition for the following compound. What is the percent of water? All right, so they're trying to ask you, now this compound is composed by this part and 6 waters. How much water? What's the mass percent of water in this compound? All right, so you can go back to the first examples. Think about how to do this. Pause the video here, and then come back here to work together with me. Alright, so the way we do this is very simple. We're going to try to find out the molecular weight of the entire hydrogen molecule first. So the whole hydrogen molecule is composed by, this is not carbon oxygen, okay, this is a cobalt. 2 chlorines and 6 waters. So you can look it up from periodic table to find the molar mass of each element. Cobalt is 58.93. There's only one of it. Chlorine is 35.45. Don't forget to multiply by 2 because there are 2 of them here. and plus 6 water, and each water is basically oxygen plus 2 hydrogen, so that's going to be 18.02. Okay, this is the water molecule. All right, so the total molecular weight is going to be 237.96 gram per mole. All right, so this is the total molecular weight of this compound. Okay, now how many grams does water molecule contribute to this? Well, 6 water molecule per mole. Okay, it's going to be 6 times 18.02, which equals to I can't really say per mole, per 6 mole water. Okay. Now, so every 1 mole of compound is this many grams, and there are this many grams of water in it. So the water percentage in this compound, or so-called the percent of water, is going to be 108.12 divided by 237.5. I'm sorry, 996 times 100%, and you should get 45.44%. So this is how you calculate percentage of water. Okay, so that solved the first subject in this video. The second subject in this video, topic in this video, I was gonna cover is to explain to you guys what is empirical formula. Okay, so the definition of empirical formula is the simplest possible formula for a compound that indicates the smallest whole number ratio in a compound. Okay, example explains this way better and easier. Okay, now for example, we have a molecular formula for glucose to be C6H12O6. Now the simplest version of, or the simplest ratio between among all of these elements would be divide everybody by 6. In this case, turn to be CH2O. So you can see there's a actual formula of this compound, and then there's an empirical formula for this compound. So that's a definition of empirical formula of this compound. Now I want to bring this to your attention that sometimes compounds has empirical formula which is the same as its original or actual formula. Sometimes it doesn't. Okay, so for example, let's discuss ionic compounds versus the covalent compounds, or so-called molecular compound. I think I wrote. Or it's called molecular compound. Now, for example, we're going to pick the simplest example. Okay, we're going to split this two. Okay, sodium chloride, which is a typical example of ionic compounds. Now, what I want to point here is this NaCl is already the empirical formula. So it is the formula of the compound, which is also the empirical formula of the compound. And the reason is that now think about a positive charged particle representing the sodium cation, another negative charged anion which representing the chloride. Okay, but the connection, or what keeps them together, is actually the attractive force between the cation and anion. So you can imagine if you have a piece of sodium chloride, which is table salt, there are a bunch of cation particles and anion particles. And for example, this positive charged species is going to be attractive to any other negative charged anion. And similarly, any one of the negative charged anion will be also attractive to positive charged cation. And then this kind of alternating pattern is going to be continued three-dimensionally. Now, the point I'm trying to make here is it's almost impossible to identify an actual sodium chloride molecule, because you can hardly tell which sodium and which chloride they are actually bonded closer than the other. So, but there's only one thing that's certain, that in the any sodium chloride compound, okay, the ratio between the sodium chloride is 1:1. So in other words, the formula of the ionic compounds reflects only the ratio between the cation and anion, which of course is the simplest ratio. So you will never see anything like this. It does not exist. Okay, so for ionic compounds, it's always going to be the same as empirical formula, the actual formula. Okay, and also I want you to keep this in your mind. Okay, you have no actual molecule of ionic compounds. It's just a bunch of cation and anions stuck together. Now, in the case of covalent compounds, it's a little bit different. Okay, let's give an example. For instance, water. Now, yes, this water is the empirical formula as well. Okay, but let's look at the water. Okay, does this really mean it's just 2:1 ratio between the hydrogen and oxygen? Well, more than that. This actually are real numbers. This represents this. Every water molecule looks like this. You have well-defined molecule of water. In each molecule of water, there are 2 hydrogens and 1 oxygen. So these numbers are real number of atoms. They're not just ratio. They are actual number of atoms in the molecule. Okay, let's give another example. We'll show a better case. Okay, there's something called a hydrogen peroxide. Usually you can find a bottle of those on the shelf of CVS or any pharmaceutical store. Okay, so the actual formula of hydrogen peroxide is this. You see, in this case, this is not empirical formula, because obviously the empirical formula of this compound should be, if you simplify 2:2 ratio down to 1:1, it will be HO. Now the reason we don't simplify this in the actual formula is because, for the same reason as water, okay? If you write out the actual structure of the compound, it will look like this. You can see there are actually 2 hydrogens and 2 oxygens in each one of the molecules. So these numbers are not ratio, they are actual number of atoms in each molecule. So that's the difference between ionic compounds and covalent compounds regarding to empirical formula. Okay, all right, so